Hey students, Mr. Sagers here, back with another video for Earth and Space Science. Today's topic is the history of Earth. By the end of this video, you should be able to construct an explanation for Earth's changes throughout its history. Let's get to it. Now, a disclaimer before we get started. Earth's history is incredibly long, and it would be impossible to touch on all of the events that have happened on Earth since its formation. That said, we will touch on a few of the major milestones that have occurred on Earth since its formation and throughout its 4.5 billion year history. The Earth formed during the same period as the formation of the Sun. In fact, it was gravity from the Sun that caused the planets of the solar system to form in the first place. As leftover gas and dust swirled around the newborn star, planets emerged out of the debris through a process known as planetary accretion. These planets accreted over millions of years as gravity pulled the gas and dust into large spherical bodies known as planetesimals. These planetesimals grew in size and eventually resulted in the planets we see in the solar system today. Unlike the Sun and the gas giants of the outer solar system, the Earth is largely comprised of solid, heavy materials. These materials include elements such as iron and nickel, as well as lighter elements such as oxygen, silicon, and aluminum. Due to its molten state early in Earth's history, elements throughout the Earth separated according to their density. The dense elements, such as iron and nickel, sank into the Earth's core or center, while lighter and less dense elements remained near the Earth's surface. This is evidenced by the fact that rocks examined from the Earth's crust are largely made of the elements oxygen and silicon, with lesser amounts of aluminum, calcium, and potassium. Throughout its long history, the Earth has gone through many changes. Earth scientists have broken Earth's long history up into useful timescales that make it easier to study. The longest of these timescales is known as the eon, which means an indefinite or very, very long period of time. Earth's history is comprised of 4 eons, which, beginning with the oldest, include the hadean, archaean, proterozoic, and phanerozoic eons. The hadean eon is Earth's oldest eon, beginning with Earth's formation and ending roughly 4 billion years ago. Much of Earth was molten during this time due to leftover heat from its formation, as well as the decay of radioactive elements. Volcanic activity was common, as were impacts from asteroids. Much of Earth's surface ran with rivers of lava. Temperatures were too hot for liquid water to condense, and the whole of Earth would have resembled a molten hellscape. The hadean eon also witnessed the formation of the Moon, most likely from the impact of a Mars-sized planetesimal with the newly formed Earth. That impact sent rocks, dust, and debris into a circular orbit around the planet. Through time, this ring of debris condensed under its own gravity to form our Moon, which continues to orbit the Earth to this day. The Archaean eon began 4 billion years ago and spanned the next 1.5 billion years. By this time, temperatures on Earth had cooled enough for liquid water to condense. The origins of water on Earth are still debated amongst scientists today, but leading theories include outgassing of water vapor from Earth's interior, as well as the impacts of ice-laden asteroids on the Earth's surface. Regardless of its source, the water could now condense due to Earth's cooler temperatures. Centuries of rain followed, resulting in the first oceans on planet Earth. Volcanic activity was still quite common during the Archaean eon as well. From this volcanic activity, Earth's first continents rose out of the oceans. Although little of the rock that made up those early continents remains today, geologic evidence suggests that the Archaean continents were made of much of the same materials as modern-day continents. The arrival of the oceans precipitated the earliest forms of life on Earth, single-celled microorganisms living in the sea. The circumstances surrounding exactly how this life came into being will be discussed in another video. But for now, suffice it to say that life first appeared on Earth 3.8 billion years ago during the Archaean eon. Although life would remain quite simple for the next 2 billion years, an important development occurred as these simple microorganisms evolved the ability to perform photosynthesis. Photosynthesis uses sunlight to transform water and carbon dioxide into simple sugars and oxygen. As these photosynthetic organisms multiplied throughout the Archaean eon, so did the oxygen in Earth's oceans and atmosphere. The increase in Earth's oxygen levels prepared the way for even more complex life to appear during the proterozoic eon. In geologic terms, the proterozoic eon is the Earth's longest eon, spanning roughly 2 billion years. During this time, the first multicellular organisms appeared in the oceans as life continued to evolve. Oxygen production increased through photosynthesis, slowly filling the atmosphere. Prior to this time, the atmosphere mostly consisted of nitrogen and carbon dioxide gases, neither of which could be respired by living organisms. The proliferation of atmospheric oxygen also led to the formation of the ozone layer. The ozone layer is derived from the element oxygen and serves as a shield that protects land-based organisms from the sun's most harmful forms of radiation. Without the ozone layer, life could have never left the protective influence of the ocean waves. With the creation of the ozone layer, however, life would eventually be able to leave the ocean and establish itself on land in the eon that followed. Several periods of glaciation also occurred during the proterozoic eon as Earth's temperatures dropped dramatically at times. During one of these periods, known as the cryogenian period, Earth's surface may have been nearly or entirely frozen, resulting in a condition nicknamed snowball Earth. Ultimately, temperatures normalized as volcanic activity produced the greenhouse gases necessary to raise Earth's surface temperatures back to above freezing. Somehow, life was able to persist through these cold periods as it found refuge in the waters beneath the frozen ice. Earth's final and current eon is named the phanerozoic eon. This eon began with a marked increase in the abundance and diversity of life, an event commonly referred to as the Cambrian explosion. In the 541 million year history of the Phanerozoic eon, some of Earth's life forms evolved the ability to leave the oceans and establish dominance on land, beginning first with plants, then amphibians. Reptiles soon followed, including the dinosaurs, and then later mammals, including humans. As plants and animals took root on land, they evolved the ability to respire oxygen from the air. This allowed them to process energy more efficiently and also enabled them to grow in size. During the Phanerozoic eon, Earth's continents continued their evolution as well. The famed supercontinent Pangaea formed and then later broke apart some 250 million years ago. Most of Earth's geologic formations, such as the Rocky Mountains, for example, were only just formed during the last 50 million years. Most of today's recognizable rivers, lakes, and seas have been around for much less time than that. Humans and their ancestors have only dominated the planet for the last 2 million years. At this point, you might be wondering how we know anything about Earth's history, given that it spans literally billions of years. To get a peek into the distant past, scientists have some useful tools at their disposal. Earth's rock layers present a detailed history of events that occurred during the millions of years of their formation. Both the type of rock and its location give clues as to how it formed and the general conditions in Earth's environment during that time. When examining rock layers, such as those seen in the Grand Canyon, the oldest rocks are found at the base while the youngest rocks comprise the top layers. Like rings on a tree, each rock layer can tell scientists about Earth's climate, volcanic activity, atmospheric composition, and even the life forms that existed at the time each rock layer formed. Another common tool scientists use to study Earth's history is the fossil record. The fossilized remains of ancient microorganisms, plants, and animals have been preserved in Earth's rock layers. By studying these fossils, geologists can get an accurate picture of what the environment and conditions were like on Earth at the time the fossils formed. For example, fossils of marine organisms found in the dry desert basins of Utah indicate that much of the land that now makes up the western United States was once underneath an ancient ocean. Fossils can also be used to determine the sequence and succession of life forms, with more complex forms of life usually appearing later or more recently in the fossil record. One final process that scientists use to discover the age of certain Earth materials is called radiometric dating. Radiometric dating is a technique that uses the radioactive materials in Earth's rocks and minerals to determine the age of those materials. Old rocks contain relatively few radioactive elements, as they have had billions of years to decay into more stable elements. Younger rocks have a higher ratio of radioactive elements, indicating that the rock was formed more recently and has thus not had as much time to decay. The element uranium, for example, is radioactive and takes billions of years to decay before it transitions into the non-radioactive element lead. If, for example, geologists study a rock that has very little uranium and a large quantity of lead, they may determine that the rock is billions of years old, having had a large quantity of time for the uranium to decay into lead. On the other hand, if a rock has a high quantity of uranium and very little lead, scientists might determine that the rock is not very old, having had relatively little time for the uranium to radioactively decay. In both of these examples, uranium is known as the parent element, while lead is called the daughter element. Scientists have used the technique of radiometric dating to determine that Earth's oldest surviving rocks are roughly 4.2 billion years old. Its oldest surviving minerals, tiny zircon crystals from the Australian outback, date to 4.4 billion years old. Meteorites from the solar system that have fallen to Earth date to 4.5 billion years old, and moon rocks hauled back to Earth from the Apollo missions date to approximately 4.5 billion years old as well. These last two examples, both the meteorites and the lunar rocks, are important in helping to determine the age of the Earth, given that they probably formed around the same time. All of this evidence from radiometric dating therefore suggests that the Earth formed approximately 4.5 billion years ago. So to recap, the Earth formed approximately 4.5 billion years ago during the birth of our solar system. Earth has experienced many changes during the subsequent history that can be categorized within its 4 eons. Scientists study rock layers and the fossil record to determine the scope and sequence of events that occurred in Earth's past, and radiometric dating can reveal the age of Earth's materials and even the age of Earth itself. Well, that wraps up our video on the history of Earth. I hope you enjoyed it and look forward to seeing you next time. Until then, ad astra.